Yeah, as Anne said, I'm here to present about the role of AI in the computer-aided engineering industry. And I would like to focus a bit on a specific project that is running right now, which is the specific application of AI in photovoltaic parks. In this project, we are currently focusing on small parks, but we are planning to scale that up to larger, more powerful, let's say, photovoltaic parks. So a few words about the company I'm working in. Its name is KYAMOS Limited, and we are focusing on the multiphysics simulations mainly, but we also have some other software for other users. And what we wish to do is actually revolutionize the market in Cyprus, which is in dire need of technology innovations. We cannot say that we are in the forefront of technology. We have our struggles, some that have been solved by other countries and not here exactly. So we have this aspiration to help a lot in our country first and then move on to larger scales. So, moving on to the next slide, an overview of what I will be presenting here now. First, we're going to see a bit about the computer-aided engineering industry, what it is exactly, because some people may not be familiar with the term. We'll move on to see the role of AI in this specific industry and perhaps talk a bit on how we have used it in the past and how we will be using it now. And then we'll dive into the funded project that I want to talk about, which I find the most fascinating of our work, let's say, and how AI is used in that. We'll have a look in just a brief look for the AI tools that we are using, and then how these tools are integrated in grid management. I guess that's a spoiler for later on. We will be using in this project AI for power grid management for electricity. Okay, so we can get started. So the computer-aided engineering, what is it? It's typically the use of computer software. You can use it for analysis of your data sets. You can use it for very complex simulations. You can use it for validation of your results and optimization of products or systems. I will give you an example here of things that our product can do. In its current state, our product, you can design using a CAD panel. You can design, let's say, for example, a room 4 by 4 by 4 meters in dimensions, let's say. You can insert windows, doors, and you can specify exactly the wind speed that's entering the room from the door or from the window, and you are setting some boundary conditions, let's say, for the problem. Then you can have two people inside that are talking. One of them has COVID. And you can use mathematical equations by giving some very initial conditions and boundary conditions to predict how the spread of COVID-19, let's say, will be inside the room in the period of 10 seconds, 20 seconds, a minute, an hour. And what we are doing differently than other industries, than other companies, excuse me, is the fact that we are leveraging the power of high performance computing to parallelize our software and our solvers as much as possible in order to be faster, yet still accurate. However, we want to make this process available to people who do not have perhaps the computational power to run the simulations. Of course, they can come to us. It is a part of our product, but it's very nice to diversify and have a product that does the simulation and might be perhaps a bit more accurate in very specific situations for some users. But for some other users, they do not require these hardcore simulations because it is also a bit complicated to set up and not just the design, but also the using the software. And we are in the process of training AI so that the user can enter very simply just some initial and boundary conditions and their geometry. And the AI, which is trained on our simulations on, I don't know, myriads of data that are produced very quickly due to the parallel processing. And that AI will be very useful for some people who just don't have the necessary expertise or are not so into research to use this hardcore software that are typically used to run the simulations. Yeah, so it is indeed very critical for industries like automotive, aerospace, energy, and manufacturing. I imagine Elon Musk has his own very hardcore simulation software for his aerospace designs and of course his automotive designs to be able to fly a rocket and then land it back, which is magnificent as a thing on its own. So what are the advantages for someone who uses computer-aided engineering? Mainly, companies are struggling with time and costs, yet they want to keep their product as a very unique and very valuable product and be in the forefront of the market, be state of the art, be accurate, be the best in their sectors. And using computing in engineering helps a lot, especially through these simulations, because instead of spending a lot of time to design the product, design a prototype, and then test that prototype. Sometimes in these industries, these prototypes are quite expensive. They may have expensive materials in them, platinum, or you can name it. So we are trying to save them time by just having them design their gadget, their engine, for example, in the software, and then run a simulation to see how would that product perform under real life conditions. So they do not need to spend that much time on the production. They don't need to spend so much money on the cost of the raw materials. And this enables them to be in the forefront of their markets and of their industries constantly. So, yeah. Why AI and computer-aided engineering? It can simplify the interface for people who are not really specialized in these design systems, but of course still need answers to their problems. It can enhance the simulations and the analysis with machine learning and deep learning, which are two things we are using in the project I will talk later. And it can enable predictive maintenance, fault detection, and process optimization. Sometimes, and we have seen it in our practices, you may not find an issue with the simulation itself, because sometimes the simulation, depending on its numerical characteristics in the code, it may converge to a result that you do not desire them to converge. But this is not for all cases. You can have one cases in 100. However, when you use an AI, given that it is trained on the correct data, that's why AI training is the most important thing. It can actually represent the physics that take place in that system more accurately, more consistently, sometimes than what the simulation would do. So, its applications, we have AI-based predictive models for system health monitoring, which is referring to the project incoming. We have optimization of designs through generative algorithms. For example, you want to design a heat sink, which this is incorporated in our thermal module of our software. If you want to optimize, for example, the design of heat sinks for a specific use, an AI is able to go through all of the possible designs and optimize the heat dissipation so that you can, again, not having to produce all those prototypes and test them physically in order to find what is best for your specific use. And of course, we can have some automation of simulation workflows, which is exactly what I've been talking about before. So just a brief non-technical unit architecture explanation. So it is the AI we tend to use the most, especially in fluid flows, in our oil spills project, where we managed to predict where the oil would spread just right offshore of Cyprus in 10 minutes, in intervals of 10 minutes. So and it worked quite well. I did not expect it to work so well, and it surprised me. And this unit architecture is quite promising. So yeah, the unit architecture typically involves segmenting the image by finding patterns in the original image, and from one image you get to 64, which is pretty much the original image, but then 64 images with the pattern that has been with a pattern that has been identified, and this process just repeats for some times, and then the unit architecture rebuilds this this image, incorporating some information from the beginning, and it can be used to predict what's going to happen in the future, let's say. We will also be using asynchronous deep reinforcement learning. This is quite novel for ourselves. We haven't used it before, but we've studied a bit, and it shows that it will be of good use. What does it do in a nutshell? You have these several agents who are interacting with the environment, and they collect some information. They can identify some patterns, and these agents will then communicate the information and update the shared neural network that's underlying the model. It is asynchronous because the different agents do not need to update the shared neural network effectively at the same time. Some agents, for example, like agent 4, they can just go back and forth really quickly, perhaps 2 times or 3 times in the period that another agent would update the shared neural network. It is quite good for larger systems that you need to identify a lot of different interactions. For example, having liquid really close to a wall or a pillar, and then like 2 meters away, you can have a liquid which is just flowing normally. Sometimes you need to update much faster to extract the pattern more easily. So in this funded project, we want to develop an AI-driven system to control and monitor inverters in small PV parks. A simple schematic is the PV park, which is connected to the power grid through the inverter. And effectively, the inverter controls whether the park is connected to the grid or is not connected to the grid. What we wish to do is to ensure grid stability and prevent faults during high energy supply periods. This is because of a very recent problem we had in this winter, actually, where we had, in Cyprus it is quite sunny all the time, but in the winter we get these very cloudy days, and it is usually a bit cloudy most of the days at least. And there was this day that we had so much sun for so long that the PV park, one of the PV parks in Larnaca that was connected to the grid, actually produced more power than what was expected during that day, and it ended up actually crashing the local grid. So this, I guess, quite highlights how important it is to incorporate state-of-the-art technology into our own infrastructure. It will improve the quality of life for people and the systems, the power grid systems health. We are starting with a very small scale as a proof of concept thing at the start of the project. We are using Raspberry Pi for all the data processing, receiving data from the inverter, sending back data, making all the decision making will come from the Raspberry Pi using custom-made software. Yeah, we have some types of data, the power, the load, the current that is being produced, and some sensor readings from the inverters. We are trying to incorporate the temperature. I hope we will be able to do it. But if it's not something very important, we may skip it. But I think it will be something useful. So yeah, and what is the automation? What we are trying to do here is the AI algorithm will be able to disconnect or connect back PV parks depending on energy supply demand, while ensuring that the system's health remains the same, that the grid is stable. We do not have any power spikes or other irregularities. So that is what I've been saying. Is the energy supply fluctuations. These are one of the key challenges. Delayed fault detection in traditional systems. Indeed, it has been quite some time since they had this issue, but it is happening, and it is expected to happen a bit more given the climate change in Cyprus. And it takes quite a bit of time to recover the system. Everyone is based in Nicosia. All the maintenance teams and monitoring teams are based in Nicosia, and they need to actually travel to a faraway location, let's say, in order to fix or reroute the electricity supply. And we have this in inefficient grid management during peak production. It is not. We do not have this advanced technology to be able at will to change which area is supplied from which substation. And through other projects that we had in the past, or let's say proposals that we submitted, they do not currently seem interested into improving their own software for grid management. So we are trying to find some other solutions for them. And exactly, our solution is to use the AI to predict these anomalies, manage the surplus energy, and optimize this inverter operations in real time, this connection and disconnection to the grid. If the AI observes a specific pattern that has before resulted to a hazard or to a non-desirable result, let's say, it will warn the user, the maintenance team, or it will act on its own, depending to what stage we reach this product, in order to optimize and keep the health of the system ongoing. Yeah, I think I have talked a bit about this. Yeah, I have talked a bit about this in the previous slides. Yes, so about the grid stability, asynchronous deep reinforcement learning can act quite quickly and helping those split second. It's not exactly split second, but those decisions that need to be made quite quickly in a very dynamic environment. Imagine the energy demand from households, from factories. It's fluctuating constantly. Everyone is switching devices on. Perhaps a huge device, a huge piece of machinery will be turned on in a factory, and this will start to drop the power for a split second. There are these huge variations in this network. It is a huge network. Definitely more in other countries and not in Cyprus, but it is still a huge one in Cyprus as well. And we need to manage to control that power output, or else it's a bit hazardous. Yeah, and what we are using exactly the unit is to detect the anomalies and predict the faults. And the asynchronous deep reinforcement learning adapts the grid operations to prevent these faults and optimize the energy flow. And of course, the outcome will be a stable grid, minimal disruptions, everyone's lives are running smoothly, no one is calling, no one is sad, everyone is happy. And of course, efficient handling of surplus energy and demand fluctuations. I just want to highlight here that one of the reasons we are doing this project is because we aim in a greener infrastructure technology, and we wish to incorporate these PV parks in our grid as much as possible, as safely as possible, because we need to take advantage of our weather in Cyprus to reduce our impact on the climate. Yeah, and yeah, the key benefits: improve grid stability and efficiency, reduce downtime and maintenance costs, real-time energy production and demand predictions, and it does indeed this project will pave the way for smarter management systems, and will demonstrate the potential of AI in renewable energy applications. And not only in that, AI is being used by very few companies for very limited amount of tasks. And however, it has started to being adopted into our public sector, with current AI answering a chatbot AI answering the customers' questions for social insurance, let's say. So it's a very specific users, and it is this project will be also sort of an advertisement to make AI for everyone, for several purposes, for several uses. So that is my talk. I don't know if I spent a bit too much time. If anyone has any questions, I'm happy to take them.